Okay. Let's start here. A few more minutes. Hopefully everyone can hear me. Let's see, is this still okay?
Hello.
Yes, Apratam. Can you hear me?
Yeah. Hi, gentlemen. So I was seeing in the class website also, I couldn't find the synopsis video. So maybe you can check.
Yeah, the synopsis video, I have some trouble because they didn't want it to be publicly shared. So I posted it on Slack. So I think if you don't have access to it, just let me know. Message me, email me. I'll get it to you.
Sorry, I thought Canvas. Okay. Hey, I mean the class.
Yeah, there was some issue with the Canvas. I was trying. I tried for a few days, but I couldn't figure it out. So it's an easier solution. Okay, we have one more minute and then we'll get started. This is a good time to ask questions if there are any. So a couple of quick things, some sample problems and their solutions have been posted, as you can see on your screen. So make sure you go through them because those are important for the midterm. Let's take a quick review on where we are in the schedule. So today, there are two topics I would like to cover, and we'll play how much we can cover. One is a very basic idea of thermodynamics. I want to go through a couple of interesting papers related to this, and then a very relatively brief lecture on optical design for recycling. And on Thursday, we'll cover some other interesting topics related to statistical ray optics and how it's relevant to solar cells as well as to anti-reflection coatings. So next week, we actually don't have class, except on Tuesday, there is a review session, again on Zoom. And of course, bring your questions there as well. And there are some sample problems here and some notes there as well. And Apratam, you will lead the review session, but I'll be around. And on the 15th is your exam. So what does that mean? That means I think what I'm going to do is I will open the exam on Canvas and close it 24 hours later. So most likely I'll open it, I don't know exactly, but I'll let you know. But you'll have 24 hours to essentially do it and submit it, and everything will be open. And it's based on the honor system, so I suggest you don't discuss with your friends. And if we find plagiarism, where the answers are basically the same, then you will be pretty severely penalized. So just giving you a warning now. So this is really just an individual effort. But you can use the internet, calculators, whatever. Just don't ask people, I guess. Any questions on the midterm before I move on?
So
everyone
I was
can hear me, right? So okay, go ahead.
Yeah, so I was thinking for the midterm review, I can also discuss the solutions of the sample problems in more detail.
Yeah, that'd be good. And okay, so that would be roughly half the first half of the semester, and then we'll go through the second half semester starting the following weekend. There's lots of really interesting stuff, but just keep in mind that your assignment 4 is due November 5th. All the instructions are already posted, so you should already be starting to work on this now. Okay, if there are no questions, let's jump right in. If there are questions, feel free to interrupt me. Okay, no questions? All right, great. So today I want to talk about thermodynamics of solar thermal devices, and maybe a good place to begin is maybe a video. So actually, let's start. And I wasn't planning on this, but let's actually start with that. So this builds a little bit of a motivation. So I'm going to play this video. For those of you who may not be familiar with this, Ivanpah is the largest solar thermal plant in the US. And this is actually pretty close to us in Salt Lake because it's between, well, it's right outside Las Vegas. So if you ever fly to California, sit on the window seat and you will see this. It's a pretty amazing sight. So I'm just going to play this. This is built by a company called BrightSource. It was built in 2003. It's right at the border between Nevada and California. And what you see here on you see a tower here, which is basically a tower which holds, at the very top, holds a black body. And all these little things that you on the ground are little mirrors that track the sun, such that the rays of the sun are essentially focused onto that black body. And the black body is essentially a steam generator. So it's water that turns into steam, and the steam essentially runs a turbine which produces electricity. So the physics is relatively simple. And this just shows the scale of it. So you get a sense for, what is this? And this is one of the most cost-effective ways of using solar energy, by the way. But of course, it's very capital intensive. So you have to build this giant, huge facility. This is, I think, more than a mile of diameter of mirrors. In fact, when you drive by, you can actually see it from the highway, 15. So this is just them showing it being built. And what's really interesting to us are the mirrors, which are also called the heliostats, which you can now start to see. They're being set up. And the mirrors have 2-axis tracking. So the mirrors comprised of pairs of mirrors, each pair essentially tracking the direction of the sun in one axis, and the other pair tracking in the other axis. And of course, the reason why I showed this, first of all, this is in the desert, so you can get very clear sunlight. And the reason I showed this before we started on thermodynamics is because this is essentially a very big thermodynamic heat engine. So we need to understand some basic thermodynamic principles in order to, for the purposes of this class. And of course, we are going to just very barely skim the surface. So if you want to learn more, I recommend taking a class to understand this. It's a very important big topic. And thermodynamics actually has a lot of connections to optics, which we will talk about a little bit more on Thursday. Okay, so what is a heat engine? A heat engine is a device or a system that converts light or fuel to heat, which is then converted to motion or electricity. So this is kind of like the quintessential form of a heat engine. You have heat input into a system. Exactly how this heat comes in is dependent on, oops, let me make sure I can, heat comes in depends upon your technology. So if you have a coal-fired power plant, you will be heating the coal, burning the coal. If you have nuclear energy, nuclear fission plant, this heat comes from a nuclear fission reaction. In the case of solar thermal, of course, you concentrate the sunlight. And that converts the water, okay, which is at a lower temperature T1. And let me change the color here. This T1 is very important, and we'll come back to that. It absorbs the heat, and then it becomes steam at a higher temperature T2. These temperatures are very important. We'll come back to that. And of course, steam occupies higher volume than water, so it expands, right? It pushes this piston, in this example, this piston, and this piston essentially runs the wheel. And the running of the wheel is referred to as the work output. Okay, again, this is a very simple idea. Of course, this is how steam engines worked and still do in many places. Heat input converts a cold object like water at some temperature T1. Now T1 is actually less than T2. into a hot object or hot side. It is steam, and steam expands, pushing the piston, which then turns the wheel, producing work. Okay, pretty simple, right? That's a heat engine. The key points to remember is that the heat difference, this T2 minus T1, is used to generate energy, and we'll come back to this. And we'll talk about a very interesting, couple of different interesting examples of that. And of course, examples that we are most familiar with in our life are coal plants, nuclear power plants, solar thermal plants, geothermal plants, where the heat actually comes from under the ground. As we know, there's some in Wyoming. Thermoelectric devices, actually, this is a very interesting example. We'll come back to that. In this example, the thermoelectric device, which we very briefly talked about in our one of the third lecture, I believe, the heat, instead of the heat input, instead of doing mechanical work as shown in this slide, is used to produce electrical energy or electrical power. So that is actually quite interesting and important. We'll talk about a particular example at the end of this lecture. But the first example is something everyone should be very familiar with, is the internal combustion engine. And this, of course, is not relevant to renewable energy, but we should understand how it works. Basically, there are 4 stages to this. Of course, there are many different versions of it. Let's look at the simplest version, which is what we call a 4-stroke cycle, or 4 stages. First stage, there's an air intake. Okay, air fuel mixture is drawn in. What does that mean? That means, okay, there is, first of all, let's think about what are the different parts. Okay, you zoom in here. So there's at the top here, you see the air fuel mixture. It's coming from the fuel source, fuel tank, whatever, into the system through a valve. Okay, and that's drawing in, that's the intake. And this is the combustion chamber where this happens. Okay, now what happens after that? You have compression. So the cycle is ongoing. Okay, so this piston is now turning this way, such that this, this crankshaft is turning that way, clockwise. So the piston is pushing up. Okay, so it's compressing the air fuel mixture. And this compressed air fuel mixture has a lot of potential energy and chemical energy, of course, in the bonds of the fuel. And an explosion is triggered by the spark plug firing. Now, of course, when this explodes, it creates gases which expand. So particularly carbon dioxide and other things, sulfur dioxide, all kinds of other pollutants and so on that we're somewhat familiar with. So this expands because of the high temperature and pushes down on the piston. And then, of course, this means that this is now turning, continues to turn, and then the valve opens, so the exhaust gases, all the pollutants come out. Okay, and the cycle repeats. And of course, this is a steady state cycle. We didn't talk about the transient. That's much more complex, and we don't really want to talk about that. But I just want you to understand, this is an example of a relatively simple heat engine, right? We use every day. Okay, now there are different ways of thinking about heat engines. There are direct conversion systems where the light is converted to electricity, right? We know this from solar cells. Or light can be converted to fuel, which is photosynthesis, right? Or there are certain types of fuel cells, but not so important. And fuel to motion is what we just talked about, internal combustion engines, right? Things like that. And there are many others as well. There's hydro, wind, tidal, everything. Any of these energy conversion systems. Now, the characteristic of a heat engine is that it is taking in energy from something, whether it's a sunlight or chemical fuel, nuclear reactions, whatever, and is doing some work on something. Okay, so there is an efficiency associated with it. In other words, how much work is actually produced relative to the amount of energy that came into the system. And this is very important, as you can imagine, and they vary quite widely. For electric generators, which is going from mechanical to electrical, is about 80%, electric motors, 90%, light to heat, 90%, chemical to heat, 90%. And solar, which is light, to electricity. Does anyone know? I mean, I assume some of you know what this efficiency would be. Any range? What you can buy today? Anyone?
Is it like 30 something percent?
The theoretical limit is about 31%, and
Right.
we'll talk briefly about it. But if you go and buy a panel, it's in the order of 15 to 20%. Right? I mean, of course, it varies depending upon where you place it, what kind of panel it is, and all that, but approximately. So those are good numbers to keep in mind. Now, what limits efficiency? This is actually an important question, right, for us. So thermodynamics is the fundamental limiter on efficiency, and we'll talk more about this again in the next class, but in some of the subsequent lectures. But fundamentally, thermodynamics places a fundamental upper limit, and this is referred to as something called the Carnot efficiency, which we'll talk about shortly. In the case of heat to mechanical efficiency, this are heat engines and solar thermal devices. The Carnot efficiency, which we will talk about shortly, is given by 1 minus T cold divided by TH hot. Now these T's refers to the temperature. So if you recall, at the very first slide, we talk about T1, T2, hot, sorry, this is cold, this is hot. So that difference is very important. Light to electric energy photovoltaic. In fact, all of these can be related to the Carnot efficiency, which we won't do today, but let's keep in mind, that's the fundamental point. Now, before we try to understand what limits this, we also need to understand some of the basic principles of thermodynamics. There's two important laws that we need to kind of conceptually understand. First is the first law of thermodynamics is essentially energy conservation. We all know this. It's written in equation form as delta U equals Q minus W. What does that mean? Q is the heat added into a system. W is the work done by the system. And the difference between them has to be the change in the internal energy of the system. Okay, somewhat common sense, I suppose. And we'll talk more about what this means shortly. The second law of thermodynamics is a little more abstract. It's essentially says mathematical form delta S is greater than or equal to 0. What is delta S? It is the change in entropy of a system, which basically means S, the entropy, always increases or stays the same. Delta S is positive, means S is always increasing. Entropy is a measure of the randomness of a system. Okay, yep, correct, yes. Entropy is very, very important in physics in general and optics in particular, because it, and particularly for solar cells, because entropy essentially determines, as we will see actually on Thursday, determines the fundamental limits on what sort of performance one can gain from a solar cell. We'll talk about some interesting concepts related to that as well. So let's dig in a little more deep. So it's a little bit of words here. Again, no need to memorize any of this, but I want you to understand this conceptually. Okay. First law of thermodynamics, we know that the change in internal energy of a system is the heat input to the system minus the work done by the system. So let's just read what it says. What does internal energy mean? The increase in internal energy of a closed system is equal to the total of the energy added to the system. In particular, if the energy entering the system is supplied as heat, and if energy leaves the system as work, the heat is accounted for as positive and the work as negative. Okay, that's fine. In the case of a thermodynamic cycle of a closed system, which returns to its original state, we'll see. So if you recall, in the 4-stroke internal combustion engine, we saw it was a cycle, right? It went through 4 stages and it comes back to the original state and keeps going. The heat Q in supplied to the system in one stage of the cycle minus the heat Q out removed from it in another stage of the cycle plus the work added to the system W in equals the work that leaves the system W out. Or if you have a closed system, the full cycle of the system is 0, because if it starts off at one state, at the end of the cycle, it reaches the exact same state. That means it is it has has no change in internal energy. Okay, so you can work out this. The heat input is Q in minus Q out, so that's coming in, coming out, plus work in minus work out. This is the work net. For the particular case of a thermally isolated system, it's also called adiabatically isolated, and we've been talking about these systems in the past where we talk about CPCs and so on. The change of the internal energy of an adiabatically isolated system can only be the result of the work added to the system, because the adiabatic assumption is that the heat input is zero. There's no exchange of heat with their surroundings. In that particular situation, the change in internal energy of the system is simply the difference between the work done on the system minus the work done by the system. In fact, this is how we actually derive the CPC performance. So you may want to go back and review that. Now, this is essentially conservation of energy, but this concept of internal energy is somewhat new to us, and it's a little bit abstract. So let's try to understand what that means in a more concrete sense, okay? So if a system has finite temperature, then its total energy has three distinguishable components. If the system is in motion as a whole, it has kinetic energy, right? We know that. If the system as a whole is in an externally imposed force field like gravity, it has potential energy, can also be magnetic field, right? Relative to some reference point in space. Finally, it has internal energy, which is a fundamental quantity of thermodynamics. The establishment of the concept of internal energy distinguishes the first law of thermodynamics from the more general law of conservation of energy. So E total is kinetic energy plus potential energy versus internal energy of a system. Now, what is internal energy? The internal energy of a substance can be explained as the sum of the diverse kinetic energies of the erratic microscopic motions of its constituent atoms and the potential energies of interactions between them. What does that mean? If I take a cylinder containing gas, what is this internal energy? It is the kinetic energy of all the molecules that make up that gas, and also the potential energy, for example, the Coulombic interactions between all these molecules. Okay, if there are charges exist, or there's a magnetic field, and so on and so forth. It's a sum total of all the internal energies of the constituent particles of whatever the system you're looking at. So, so it depends on how you define it. You can define the entire solar system, right, or something like that. By the way, this concept of both the conservation of energy and the increase of entropy were critical to the Nobel Prize in Physics that was announced today morning. So you may want to go and read the news public release, because Roger Penrose essentially applied the principles of entropy to with the theory of general relativity to predict the develop the equations for predicting black holes and so on. So anyway, so it's an interesting aside since it's very timely. So these microscopic energy terms are collectively called the substance's internal energy, U, and are accounted for by macroscopic thermodynamic property. The total of the kinetic energies of the microscopic motions of the constituent atoms increases as the system's temperature increases. We know that. If you heat up a gas, it's going to move more, so its internal energy increases. This assumes no other interactions at the microscopic level of the system, such as chemical reactions, potential energy of constituent atoms with respect to each other. Okay. Not terribly important. So now let's step back and understand what do we mean by work. Work is a process of transferring energy into or out of a system that can be described by macroscopic mechanical forces exerted from outside the system. For example, the piston was compressing the gas in the internal combustion engine. That is work done on the system. The gas expanded upon an explosion and pushed the piston out. That was work done by the system, but if we call this the gas as a system. Okay. And of course, flow of heat is also a form of energy transfer. As we know, if you have conductive heat, convection, or radiation, for example, in the case of a solar cooker, you have flow of heat that causes loss, right? So it's obviously an energy transfer. Now, second law of thermodynamics indicates that natural processes are irreversible. So we kind of know this, and I assume you have all seen this in your high school physics. If you take a teacup, drop it on the floor, it breaks apart. Why don't the pieces of the teacup come back together and form the teacup again? This is because of entropy. The fact that we grow old is related to entropy. The fact that the time has a direction is related to this entropy as well. So all of these are very, very important concepts, but of course, not directly related to what we are talking about. One very important thing we need to understand is that when we talk about thermodynamic equilibrium, temperatures tend to equalize. Now, I'll give you two examples of this. One, of this idea of entropy, right? One is if you take a very hot object and touch it to a very cold object, okay? Eventually, if you give it enough time, they both will reach the same temperature, right? Assuming there's nothing else around it, it's completely isolated from the universe. They will both be the same temperature. Okay, so that's an example of entropy increasing of the whole system. In this case, if it's completely isolated, the entropy is equal, basically. Cold objects has a lower entropy, hot objects have a higher entropy, and the sum total of this entropy will be same as the total of these two. Another example is in desalination, right? Remember, we had the example of a system comprised of very salty water on one side and pure water on the other side, and you had a membrane. This salty water has a lot of salt molecules that are floating around, so very high entropy. The pure water has very few salt molecules floating around, low entropy. So the salt molecules will the water molecules will go from here to here, right? Eventually, actually, it depends on what this membrane is, but let's imagine the membrane allows salt to pass through as well. So it's not a good desalination system. Eventually, both of them will become salty. Okay? But at a lower saltiness than here, but higher than here. So that's an example of another equilibrium situation. Yes, go ahead.
Sorry. First of all, entropy drives me insane. But is it basically just like a difference in states?
So it's a good question. The mathematical definition of entropy is a little more complicated than that. You can think about it essentially as the potential degrees of freedom in a system. So in different physical systems, entropy has to be defined differently. But think about, for example, let me see, what's a, well, yeah, I don't have a simple example, but an example would be this, what I just said. So for example, the salty pure situation, the salty side has a high entropy because you have a lot of salt molecules floating around on the left-hand side. On the pure side, there's very few salt molecules, so they're very relatively low entropy. And what that means is that there are fewer molecules that can occupy different energy levels and different kinetic energy levels, for instance.
Okay, right. So just like differences in like potential energy, sort of.
In this example, I'm ignoring potential energy. It will just be the kinetic energy. Another way to think about it is if I have a single atom at 0 Kelvin, that has zero entropy essentially, because it is doing nothing. It cannot move. But as I increase the temperature, it is going to it's going to move around, right? Because of Brownian motion and diffusion and so on. This can be referred, in the absence of anything else around it, that can be simply thought of as kinetic energy of that atom. And that is increasing the entropy.
Okay.
And another way to think about it is the entropy is also the driving force for the expansion of the universe, because things are moving further and further away, not only moving further away, but they're also moving faster. They're accelerating. So that's an increase in the kinetic energy. But okay, from our perspective, we just need to understand this a little more qualitatively, I would say. It's very important. And I will also make another quick comment, which we'll come back to. If you recall, in the case of the CPC, there was an acceptance angle with which we can concentrate the light. And this acceptance angle is directly related to how much you're concentrating. In other words, if you want to concentrate more, you have to accept less. This turns out, and it's kind of hard to think about it right now, but you can actually show this is essentially a conservation of entropy. If you, and let me make a hand waving argument. I'm not going to make a full mathematical argument. If you have a very small cone of rays, okay, very, very straight cone of rays, I can concentrate it really, really highly because I have very low entropy. All the rays are pointing the same way. And if I, oops, sorry, let me just erase this. But if I have many, if I have a larger acceptance angle, I have a larger entropy here because I have many possible directions of rays, so I cannot concentrate it as much. And that limitation actually can be tied to the fact that if you cannot decrease entropy, there is no way for you to take this large entropy situation and put it into a very small receiver, which is a low entropy situation.
Okay.
That's a conceptual way to think about it. Mathematically, it's a bit more complex than that.
Very cool. Thank you.
Yeah, so it's thermodynamics is a very beautiful theory because it applies to many things, you know, everything from quantum mechanics to relativity to optics, as you could imagine. Okay, so from our perspective, you know, we just need to understand this basically. So let's just go through this quickly. When two initially isolated systems in separate but nearby regions of space, each in thermodynamic equilibrium with itself, but not necessarily with each other. So that's the example that's shown up here, for example, right? Are allowed to interact, so they're touching. They will mutually reach a they will eventually reach a mutual thermodynamic equilibrium, which is the state I'm showing on the right-hand side here. The sum of the entropies of the initially isolated systems is less than or equal to the total entropy of the final combination. If you have a perfect isolation from the universe, then it will be equal. If you have some loss, it will increase, the entropy will increase. Equality occurs just when the two original systems have all the respective intensive variables, temperature, pressure equal, then the final system also has similar. Okay, that's just detail. But in any case, I just want you to make sure you understand this conceptually. Now let's apply these ideas to heat cycles and heat engines, okay? Now, again, just to remind ourselves, a heat engine is nothing other than a system that does work. It takes heat and does something with it, okay? For example, a reverse osmosis is also a heat engine, right? You're pushing on the membrane and pushing the water through. So you're doing work on the system. So it's not just the heat, it can also be mechanical work. So but the conceptual picture is as shown here, okay? You have a source at some temperature, TH. Now this refers to hot, okay? Q in is the heat coming in. And then you have this green circle here, which is the heat engine. It does some work, which is the important thing we're interested in. And then it also spits out some heat. So this can also be a refrigerator, for example, right? We saw that one of our early lectures, to a sink. The difference between this hot source and the cold sink is the most critical thing that determines the efficiency of such systems. Now, you can think about this in terms of cycles, and this pressure volume diagram is a nice way to think about this in the case of gaseous systems, like the internal combustion engine, where you have a gas that expands and contracts and so on, right? Also in the case of the refrigeration, where you have a refrigerant that expands and contracts as compressed and so on. So it's very similar. And this is called a Carnot cycle. So you have two variables here. The horizontal axis is volume. The vertical axis is pressure, okay? As we know, as volume increases, pressure decreases. So it makes sense. As volume decreases, pressure increases. All of this makes sense. Now, let's look at a cycle. So I'm gonna start here, and you can start at any arbitrary point. I'm gonna go this way on this curve, which is isothermal compression, which means that in this ideal situation, temperature is maintained at the cold TC, and by the object is compressed. Okay, so this is the piston pushing against the gas. This is when the heat comes out. Okay, that's this in the case of refrigerator, this is a situation where the heat is drawn out of the system. Remember, that's when you compress the gas, the gas condenses and becomes liquid. It draws the heat from the refrigeration. And then you have this blue part here, which is referred to as adiabatic compression. So again, the volume is decreasing, but it's decreasing in a very special way. There's something called adiabatic. Won't talk much about that for now. Pressure is increasing until it reaches some point there. Now you allow it to expand. This is in the case of the refrigeration example. You're allowing essentially the gas to expand through a valve, if you remember. So that's this red curve here. And it's also called isothermal expansion. And the ideal case, this is at the hot temperature. So it's hot, okay? So it's essentially drawing the heat into the system. Okay, so it's expanding because it's, remember the compressed liquid in the case of refrigeration, the gas became a liquid. Now you're allowing it to expand. It is taking energy from outside and then becoming gas. Okay, so that's that expansion. And then there's an adiabatic expansion. Again, the adiabatic parts are not terribly important for the sake of this discussion, but it's very important from a thermodynamic point of view. Anyway, so this cycle, the energy of the cycle, by the you are probably familiar with this fact that the energy units are pressure times volume. Of course, it's proportional. There's some factors here, 1/3 and so on and so forth, but it's not so important. So the units, so that you can see that the area under this curve, which is this pink part here, this stuff, is the work done by the system, or the total energy expended by the system, okay? So you can see Q out is here, and Q in is here, and whatever is remaining is this very important thing called work, and that's the area inside this curve, okay? And we'll define the efficiency shortly. And then there are, of course, different ways of drawing the cycle. That was just the Carnot cycle. This is something called the Stirling cycle, slightly different Stirling engine. In this example, you can see if again, it's still a volume pressure curve. Let's imagine I start at this point. I'm gonna go up here. So I'm decreasing the volume, increasing the pressure, just like before. This is where the heat is spit out of the system. And then here there's a constant volume. So the volume is fixed, but increasing pressure. So it's a very interesting situation. And then from that point, you allow the fluid to expand. Again, heat is drawn from outside the system into the system. And then you have a constant volume compression. So constant volume decompression. So pressure is decreased where the volume is fixed. So slightly different situation, and you can actually show the area under this curve, which is the work done, is always less than the work done in the case of the Carnot cycle. So Carnot's theorem essentially says that all irreversible heat engines between two heat reservoirs are less efficient than a Carnot engine operating between the two same reservoirs. And that's the efficiency number here, which is again 1 minus T hot divided by T cold, which is of course T hot minus T cold divided by T cold, right? Which is equation. Whoops, my mistake. Let me redo that. Let's erase. Confuse. Don't want to confuse you guys. So, of course, the hot has to be at the bottom, otherwise it would be more than one. So this is H, or negative, sorry. Right. Hot has TH is greater than TC. So, okay. So this point, the Carnot theorem states that all irreversible heat engines, which is all real heat engines, between two heat reservoirs are less efficient than a Carnot engine operating between the same reservoirs. It also implies that all reversible heat engines between irreversible, this is a typo, between two heat reservoirs are equally efficient with the Carnot engine operating between the reservoirs. This is a consequence of the second law of thermodynamics. So far, we've thought about this very abstract sense, and hopefully you have a qualitative picture now. Now let's try to apply it to something real, okay? The efficiency of a solar collector, which is similar to the first video that we saw, okay? So what is a solar collector? Well, what are we talking about here? We have a collector, which is like a CPC, let's call it, which has an area of A times C. C is the concentration factor, geometric concentration factor. And then let's imagine you have a black body, some sort of absorber, solar cell, or the black body that you saw on the tower in the video, which is just an absorber area A. So you can see the ratio between these two, the geometric concentration is C. Now the question is, what is the Carnot efficiency? What is the absolute efficiency of such a solar collector? And let's try to calculate it. First thing we know, of course, is that the Carnot efficiency, 1 minus Tc over Th. Okay, no problem. The area of the collector, which is the efficiency of the collector, is simply the heat absorbed by the collector minus the heat lost by the collector divided by the incident heat on the collector. Okay, so far so good. Now we need to figure out what are these terms. So what's the heat loss? Heat loss, as we know, we are going, for simplicity, we're only looking at radiative heat losses, and we're going to look at Stefan-Boltzmann law, which we saw before. It's simply the emissivity multiplied by the Stefan-Boltzmann constant, sigma, multiplied by the temperature raised to the 4th power, and its temperature is the H, which is the collector area. The collector temperature, let me see, TH. I think that is correct. I just want to make sure I didn't make a mistake. Okay, yeah, I think it's correct. And A is the area of the collector, so that's the amount of heat that's lost by radiation. And what's the incident energy? Which incident on the solar cell is simply the area of the collector multiplied by the concentration factor times the intensity of the solar insolation. So we can now write the eta collector as 1 minus Q, so Q lost, which is this term right here, divided by the incident. And here I'm assuming that the absorbed is 100%. So it's taking the ideal case. So this essentially becomes the same as the incident, essentially. It's not exactly true, right? We know that, but let's just say for the sake of this argument. Now we also know that there's this absorber has to do work on it, so it has a Carnot efficiency as well. So the total efficiency of the system is the collection efficiency multiplied by the Carnot efficiency, and you get this nice expression. Okay. Now we can plot this expression, is shown by this plot here. Let me show the expression as well. As a function of the hot temperature, and the vertical axis is the efficiency. So in each curve here, you can see as the temperature increases, as the temperature increases, the efficiency increases. But there is a maximum efficiency that you can attain because of the losses, right? You can see at very high temperatures, you have high losses as well because of this T to the power 4 term. So that's why you reach a peak and go down. And this, these different curves here are increasing concentration, increasing C. So now you can see a very interesting thing. By concentrating the light more, I can get higher efficiencies. So this is a concentration factor of 10. My best efficiency I can get is maybe, let's call it 25%. But by increasing the concentration factor to 50, I can get, maybe 41%, and so on and so forth. So that's a very nice thing, right? So you want to concentrate more light. But keep in mind, when you concentrate more light, that means you also need to maintain high temperatures or handle the high temperatures, so it becomes more complicated. Okay, so it's a simple example. Now we talked about this, and I'll show you one other quick example. So there are many different ways of implementing the solar thermal systems. Usually they're very large systems. An exception to this are the solar water heaters. So some of you probably have seen these on rooftop, right? Roofs. So these are fairly, this is the exception. So these are fairly small scale systems. But I'm showing you here pictures of very large scale systems. So this is an example of a Sandia dish, Stirling engine. This is from Sandia National Labs. Efficiency of about 30%, very high concentrations, 2000, very high temperature, so you can see 700 degrees. And some large installations are starting to appear. This is a very nice system, very large power tower in Spain, and I have a quick video of that. This is a very large system with about 11 megawatts peak operating power. Of course, one of the big challenges of such systems is that they don't work at night, so you need to somehow store it. And the way these guys, is a company called Abengoa, the way they solve this problem is by essentially using molten salt. So they put, instead of steam, they took sodium chloride or some plus some other stuff, and then melted it. It was so hot that it melted it, and then pumped it underground and stored it. And that then can be run at night to produce power, or at least part of it. So let's see. Let's play a quick video. And while I'm playing the video, I want you to think about identifying some problems with these systems that you can think of. And I'm going to put you in a breakout group to discuss that briefly, but let's quickly play this video. How do I get out of this? Get out of that. Play. Yeah, this is oh, this is a different system. Solid car in Sevilla, in southern Spain. So you can see the massive mirrors, the heliostats. They're generally quite large. In fact, one of the last lectures is a guest lecture from Google, where they actually developed very new, interesting technologies for these heliostats. So keep this in mind. So pretty big systems, tens of megawatts. And here, this is an interesting situation where they have some combination of solar cells. So the solar cells with some reflectors, in addition to the heliostats. So it's an interesting situation. And this, I want to point out one very important thing. This arrangement of these heliostats, some of you might say it's reminiscent of sunflowers. And that's exactly true, because it's a fractal arrangement which depends on the latitude of the location, but it allows you the most efficient coverage of, because you want to essentially minimize shading between the heliostats while maximizing the aerial coverage. And that turns out to be this fractal arrangement, which of course evolution has done for sunflowers. Let's see. Okay, some nice, pretty pictures. So you get the sense of it. And this is one-sided, so it's kind of interesting. There's nothing on the other side. So. Okay, let's see. Is there anything? Nope. Okay. So I'm gonna come back here. And that's the end of our very, very brief introduction to thermodynamics. I want to take whoops. I want to go back and use this opportunity to put everyone in breakout rooms. And I want you to discuss the following question, which is, so I'm gonna go back here. We saw all these big, large-scale power plants, right? Solar thermal power plants. Can you discuss some of the problems? So similar to what you did for your assignment 2, I want you to do this in small group. So we'll spend a couple of minutes on this, and then I'll bring you back and ask you to summarize what you discussed. Let's see if I can. Why is it? There we go. Okay, I'll give this a shot. Okay, sorry, I guess I must have got disconnected. Can you guys hear me still? Yes. Hello. Hello.
Yeah.
Yeah.
Yes.
Okay. Sorry about that. So my question was, did anyone identify any interesting problems?
Yeah, our group
Anyone?
said that it's probably the maintenance of all the mirrors.
Yes, that's a very good point. Yes. Because it's a desert, so obviously it'll get a lot of dust and things like that. So yes, great, good
And
point.
also-
We're
and
saying
also
that
moving
the
parts.
construction must be very expensive also, like to construct all of that. It must be very expensive to build that, also the cost.
Yeah, that's definitely true. But that's why you go for scale. So you make these huge, so you can produce a lot more electricity because you amortize this cost over lots of watts of power generated. But that's definitely a problem. Yes, that's one of the reasons why you don't see a lot of these, obviously. But
And then our group had one other thing was the transmission or the area that you had to cover. So like you can't put it in the middle of a city, so you have to transmit it all the way to the
Got it.
city, which
yeah, great point. Yeah. And related to that would be environmental concerns, right? So you can imagine you have to cover this habitat over such a large area. And obviously these places, as we know in Utah, are pretty sensitive. So that's definitely a big concern as well. And transmission losses, as you pointed out. Yeah. What? Yeah, go ahead.
Oh, sorry. I was just going to say one thing our group was talking about was the availability of materials as well. Like a lot of the rare earth metals that are used in this are like 90% of rare earth metals are produced in China, and they've stated that they, a lot of their current supply could be exhausted within as close as 20 years.
Yeah.
So there may be material switches or different types of materials that will need to be investigated for viability instead.
Yeah, completely. Yeah, that's an important point. But I would say this is more important primarily in the high-tech industry, electronics and so on. In the case of mirrors and so on, you don't need too much rare earth, but maybe in the power electronics, I suppose, in the turbine design and so on. But definitely, it's a very valid concern. Yeah, agreed. So materials are, and related to this, I would also add that one of the biggest concerns is the cost, right? Which kind of was mentioning also. And if you think about the cost, the biggest cost turns out to be all the mirrors, the heliostats, because you have to have a huge numbers of them. So, reduction in price of the mirror by a small amount can make a huge difference in the cost. But these are very simple, relatively low tech materials, like silvered mirrors or glass and aluminum frames and things like that, right? One thing we didn't think about is wind loading. So because the mirrors have to actually tilt, I don't know if you can see my hands, but if there is big wind storms and so on, they can break off, right? And that's problematic. So wind loading is very, very important in these designs. We didn't talk about that. That's quite critical. Okay, in the interest of time, we have to move on. I want to talk about this particular paper. This is a very beautiful piece of work by someone I know, actually, Shen-Hui Fan. Very, very sharp guy. He's a professor at Stanford. He showed, and there's a series of papers, but I will just highlight this particular work, which is because it's related to heat engines we talked about today. Okay, this, first of all, the title itself is pretty intriguing, right? You're generating light from darkness. So in a nutshell, what this is showing is a solar cell that works at night. So again, quite dramatic if you think about it. Now, what does that mean? And this is something you can understand based on what you've seen in today's lecture. It's a heat engine. It has a cold region and a hot region. So let's see what those things are. So from the schematic, the whole oops, let me take that. Okay, so the cold region is simply the cold of space, which is typically around 3 Kelvin, very cold, right? And the hot region is the ambient air, which is around 300 Kelvin, slightly less. So this is now my TH, and that is now my TC. and you're essentially building a heat engine that performs work between them. Isn't that such a clever idea? And of course, the details are important. Here they have something called a radiative cooler that radiates the heat out into space. So it cools one side of this thermoelectric generator, while the other side, so that's the cold side, and the hot side is essentially attached to this aluminum heatsink, which thermalizes it to the ambient temperature. So that's the hot. And because the thermoelectric generator, as we saw in our third lecture, generates electricity from a difference in heat, it can be used to power an LED. So essentially, by putting this device, it's a very simple, cheap device, you put it on the roof at nighttime, it produces enough energy to run an LED. So really clever, really interesting application of the principle of heat engines. So let's, and I posted this paper, and I highly recommend everyone to read it, but I will highlight a couple of figures here. First of all, the system is very simple. As you can see, it's just a piece of polystyrene with all of this is just bought off the shelf with some reflectors. And this thing right here is simply a, this radiative cooler is also bought off the shelf. I forget exactly what it is. It's, let's see, it's here somewhere. Let's see, it's just a aluminum disc painted with a commercial black paint. That's it. It's a very simple, right? Very clever idea. And there's, of course, the most expensive part here is the thermoelectric generator, which is also just bought from some catalog. And the whole thing is only like $20 or $30. And that's it. It's very simple, right? And you can see the electrodes coming out, producing electricity. Oops. Let's see, what else can I show here? Oh yeah, here you can see the LED working at night. Again, this is pretty incredible. Light is being generated from darkness. That's the title of this paper. Pretty amazing, in my opinion. So, an example of a very clever application of heat engines. Okay, so the remaining part of the class I want to, and this will be fairly short, I want to talk about a very different field where optics is applied. Whoops.
I have a question really quick.
Mm-hmm. Go ahead.
Since this is generating like electricity from darkness, could it somehow be coupled with a solar plant to generate electricity at night?
Yes, so if you read the paper, so those are the ideas. And in fact, the idea is to make it modular. So imagine this is cheap. So you can imagine having something like this in a poor village, because you can potentially scale it up, or a whole village or a house, and have light. So you can, kids can do their homework at night, for example, right? But of course, you can also couple it to PV during the day to get, with storage for electricity and so on. So all of these vision are described in the papers, and a couple of papers before that. So it's on our website. So feel free to actually, let me just make sure it is. Yeah, it's right here. So you can see I posted it right there. So you should be able to get it. So I highly recommend you to read it because it's very interesting. Okay, so I want to talk about recycling, because recycling is a very, very interesting industry. And since we don't have a ton of time, I want to go through this fairly quickly. Optics plays a very major role in recycling, and recycling is a major problem, right? And then, as you can imagine, very small percentage of objects are actually recycled. And if you think about all the plastics, there's a prediction that in 2050 there will be more plastic in our oceans than fish. So these are big, big problems that need to be solved. And I just want to highlight a few applications of optics. So this is from a paper that also posted on the website. In many countries, primarily Northern Europe, Finland, Germany, Sweden, and so on, there are big government subsidies for this. So, you have these deposit schemes where you put a bottle or can back into this machine called the reverse vending machine, and you get some money back or a credit or whatever. In the US, not so popular, I think. So the big challenge is that once you get this stuff into this machine, how do you identify and sort the waste at very high speeds into multiple categories for recycling? And that's where optics comes into play. And sorting is very important, because the more precisely you sort the materials, you get more money for it. It becomes more valuable. By the way, this is also relevant to one of the points someone mentioned about rare earth materials, right? How do you do recycling of electronics? Because there's a ton of rare earth materials in all the electronics. So, I won't talk specifically about it, but it's actually quite critical that we recycle these instead of putting them in landfill. One approach is to do shape measurement. So to be able to distinguish between a bottle and a can, for example, typically you pass them through conveyor belts, and you have photodiodes on each side of the conveyor belt as shown in the bottom figure. And by looking at when the signal is interrupted, just like you see in a garage door opener, right? You have the security feature. By interrupting that signal there's a laser on one side and the detector on the other side, which is not shown. If you interrupt the signal on the detector, you know that there's something between the detector and the source. And by timing it, you can figure out the shape. This, of course, has to be done in a very high speed and things like that. A more accurate approach is something called laser range finding. Essentially, a laser is modulated and it's reflected off a target, and the distance from the target is measured. Now, this is an example of how that's used in a crate, where the laser actually moves in a semicircle and you measure the shape of the material. Now, you might be more familiar with this in the form of LiDAR. So let me just play a quick video of LiDAR, because LiDAR is actually now very important for self-driving cars and so on. So I just want to make sure everyone's aware of this. So let's play this very quickly. I won't play the whole thing. But nowadays you can fly these drones and airplanes and essentially get topography at very large scale. Of course, you can also do the smaller
LiDAR.
scales. For instance,
Light
in
detection
the
and
latest
ranging.
version of the iPhone, it's
LiDAR is a
supposed
remote
to have
sensing method
something
that
like this
uses
on a chip,
laser to measure
essentially.
elevation.
So this is
like
not only
ground,
applicable
forest,
in these
and
very
buildings.
macroscopic scales, but also in small scales. For instance, to map out your face, to recognize you, or map out a room, or whatever, in the case of the phone.
LiDAR
So,
uses ultraviolet, visible, or
let's
near-infrared source to sense objects.
Turn this up.
Light energy emitted by LiDAR system is known as pulse. Light reflected from ground or object is known as return. This means the LiDAR system sends a pulse of light and it waits for the pulse to return. It measures how long it takes for the emitted pulse to return back to the sensor. In the end, it gets a variable distance of the objects. Actually, this is how LiDAR got its name: light detection and ranging. Like sonar uses sound waves to map things, radar uses radio waves, a LiDAR on the other hand uses light sent out from a laser. A LiDAR unit scans the ground from side to side as the plane flies. Because of this, it covers a larger area. While some pulses will be directly at nadir or a straight line, most pulses travel at an angle. Airplanes, unmanned aerial vehicles, and helicopters are the most commonly used platforms for acquiring LiDAR data over broad areas.
Okay. So you can also do this from space and so on. But of course, what's most exciting is, let's see, oh, they don't show it here. Okay. So what's most exciting to some extent is that all the self-driving cars, other than Tesla, actually uses LiDAR on top of the car, right? You've probably seen that little dome. That's exactly this technology. So this technology actually is also used, and originally was used in the recycling industry. Of course, you can do shape recognition with cameras and image processing. We'll go into the details of that. But one important point I want to make about the recycling industry is that the market's very interesting. And this also is relevant to your project, because this is an example where the market affects the technology. You can have many different ways these things have to be implemented, whether it's a single use versus multi-use containers, whether it's a container deposit. If you have a container deposit like we do in many states in the US, for instance, I used to live in Massachusetts where there was a 5-cent container deposit on aluminum cans. And when you return them, of course, you can get that 5 cents back. But of course, lots of people don't return them. And simply that 5 cents essentially goes away, right? Now, where does that go? It remains in the system. So so let's say I already paid for a can of soda, but I did not reclaim that 5 cents. That 5 cents is now within the recycling system. And that interesting situation means that the non-participants, but the fact that I don't participate in the system, I can actually finance all the operations. It's actually quite a large amount of money. So if you have 90% of participation, 10% of deposits are essentially profit, right? Then they're used to finance infrastructure and operations. In non-deposit markets, like in Utah, for instance, we don't have deposits. The commodity prices essentially drive the industry. So the purer the plastic is or aluminum is, then you can charge higher price for it. Accurate sorting and efficient transportation are key driving factors. So these are all important business inputs that will drive the technology.
I'm so sorry to interrupt you, teacher. I think there's a question. I think there's a question on the chat.
Yes, Nick, that's correct.
Yeah.
Difference. Yeah. Well, there's a little more detail than that because radar. Well, yeah, I think more or less it's just the difference in the wavelength. Radio waves are, of course, much longer than light waves. Now, this is the reason, by the way, why we don't use radar in self-driving cars. It's just that there's not enough resolution. Radar is great for detecting aircraft, but it's not good for detecting an animal or a person. You know. That's why you have LiDAR.
Cool.
Now, coming back to the lecture, recycling plastics is challenging because all the plastics look the same. So how do you distinguish between the different types of plastics? You have to do something called spectroscopy. This is where optics comes in. Essentially, what that means is that if you look at the transmission of light through different kinds of plastics, polycarbonate, this is glasses made of PET, for example, polyethylene, all these different things have their different signatures. So this is transmittance through this plastic as a function of wavelength or color. This is in the near infrared, so it's about 1.5 microns. So you can see they have these different signatures. So by measuring the signature, you can very quickly say, okay, what kind of plastic it is. And there's lots of technologies which do this. I won't go through this in any great detail. A very simple technology is to have a filter wheel with the different plastics placed in it, where you can see here, here, and here, and so on. And then you simply pass a light through it, a broadband light and a detector on the other side. And if the light passes through the plastic, then that registers on the detector, and then you know that there's a particular plastic. In fact, sorry, so there's a source, then there's your sample, and then there's this filter wheel, and then there's a detector. So and this is spinning. So by looking at the signal on the detector, you can tell what kind of sample this is. This is an example of one such machine that does that. By the way, the article was written by the founder of this company called Tomra, which was based in Norway. I believe they're being acquired by some other company now. Let's see. You can also do this in a very clever way using something called diffractive optical elements. I'm not going to talk about this in the interest of time. Of course, the key things are you have to do this at a very large scale. So if you want to, these things have to be done at the municipal scale, right? So very, very large scale, very high throughput, so very large speeds. And we'll show you a quick video about that as well. So for example, you have to do 30 tons of waste per hour. You want to look at near infrared visible spectra to do, distinguish between colored plastics, transparent plastics. And again, in non-deposit markets, this is driven primarily by the costs, right? Material costs. So this is all numbers, but you get the idea. PET costs, aluminum costs, things like that. Aluminum can be melted and recast into containers and other items. PET, for instance, can be turned into fiber, used for fleece, fabrics, etc. Nowadays, there's also recycling of textiles as well, which is much more complicated. So this is an example of what's called a material recovery facility, MRF. Let's actually look at, okay, so that's my last slide. Let's look at a couple of videos. So first we'll start with the MRF. Again, the purpose of this particular lecture is for you to be aware of these technologies. So I'm gonna play this. So this is New York City, probably one of the largest recycling centers in the world. And the US. Okay.
This is New York City's main recycling facility. We take in all of the residential recycling in bins and bags throughout the 5 boroughs. Comes here and we sort it out.
So sorting is the important part where optics plays a major role. It's separating as shown there. Magnetizing removes the metals, as you can imagine. The sorting in that example was done by humans, which is of course a very bad way to do it. Dangerous job, very slow. So optics is making it automated. So those reverse vending machines we talked about before primarily dealt with glass because of glass bottles were much more common in Europe in the early 90s and 80s. So that's a magnetizer, as you can see. So you can see the ballistic sorting means that you have to identify what it is. So there's a very high-speed camera that's identifying those plastics. That's optical sorting, which is what we just talked about. And of course, human sorting, which is not good. Okay. And of course,
we're really working within this zero waste by 2030 goal. We need to make sure that everything that's out there that is recyclable gets into a bin, gets into a bag, makes its way here, and that we have the capacity to process it.
okay, I think I can stop there. So one very important thing that happened in the recycling industry in 2017 or 2018 is that China decided not to take in recycling materials from the US. So it's an even bigger problem that we have to solve. And I want to just point out that this is also a big industry. And there's one more white paper, and I'll stop. I actually posted this white paper on the website. So this is from a company called Spechem, which is a company that makes a special type of camera based in Finland. And they use this for various kinds of recycling. It's a special type of camera. It talks a little bit about the details of the recycling industry if anyone's interested, and the goals of the industry. But let me just highlight this camera is called a spectral camera, which you can read about here because it not only sees the intensity of light, but also gives you the wavelength information. So if you recall, in one of the previous slides, I showed you the spectral signature is important to distinguish between the different plastics. This is a camera that allows you to essentially do that in one shot. So these are examples. So here you can see different, on the bottom on the conveyor belt, different bottles are passing by, and they have the Spectrum camera, which is, you have see this nice illumination and so on. And it will, the PET and PVC look the same to a human eye, but the special camera, you can actually tell them apart, as shown by this, this little computer monitor here. And then you can sort it out. There's a robot that takes the PVC out of the example. That's plastic recycling. Plastic recycling is very problematic because, like I said, like I said before, by 2050, it's estimated there will be more plastic in oceans than fish. So this is something we do have to solve. And I believe technology, particularly optics, can play a big role. So just another thing to keep in mind in the case of in recycling, we have these numbering schemes 1, 2, 3, 4 to 1 to 7, which represent the different plastics. And so in one of the years that I taught this class, a project team actually took it upon themselves to just essentially create a smart recycling bin that had a camera and some image processing software that will essentially read this and separate it directly in the household bin itself. So that simplifies the situation for the municipal processing facility. So that's a really nice, clever innovation that team worked on. So these are examples of text plastics that are black, which are really hard to sort. So showing that the particular camera can actually see infrared light, which allows them to do the sorting. And finally, sorting of textiles is going to become compulsory in Europe. In the EU, I think in 2025. So they are working on some interesting technologies to be able to separate natural fibers from synthetic fibers and these different fiber groups as well. And that's a very hard problem. And that's it. And I will actually stop here. So in today's lecture, what I really wanted to do was to give you a sense of two things. One is to give you a very brief overview of thermodynamics, so kind of understand it conceptually. And number two is give you an example of application of optics in in industry that you may not have thought about before. So I just want you to appreciate the innovation and the scale of the problem that exists. So certainly, we need lots of smart people like yourselves to think about these problems to solve, and hopefully optics can play a major role. Okay, if there are any questions, I can take them, and I know we're basically out of time, but I can stick around. Okay, guess no questions. Okay, again, I recommend reading the lecture notes and the white papers. They're all posted on the website. And of course, if you have any questions, post them on Slack anytime. So I think I'm going to get rid of this set office hours because it doesn't make sense. So you can post your questions anytime on Slack you want, or email me anytime you want. So I usually get back to you pretty quickly. Okay, and start studying for the midterms because that's next week. So, all right, stay safe. All right, take care.
Thank you.